At 7 in the morning, the first thing some drivers in Wyoming saw was not sunlight. It was white, a wall of snow moving sideways across the highway, swallowing road signs, headlights, and entire vehicles until the world outside the windshield became nothing but wind and ice. Truckers slowed to a crawl. Families pulled over. Highway crews watched conditions collapse hour by hour as a spring morning turned into something that looked like the middle of winter. But almost 2,000 miles away, people on the East Coast were waking up to a completely different emergency. In Boston, New York, Philadelphia, Baltimore, and Washington, forecasters were warning about heat that did not belong on the calendar yet. The kind of heat people expect in July. The kind that pushes pavement temperatures higher, fills emergency rooms, and catches people off guard because their bodies have not had time to adjust. While one part of America was disappearing into snow, another part was preparing for dangerous early season heat. And between those two extremes, the atmosphere was becoming even more unstable. Across the plains, storm chasers were watching computer models with growing concern. The ingredients for violent thunderstorms were beginning to come together. Warm, moist air was moving north. Cold air was pushing in above it. Winds were changing direction with height. The kind of setup that can turn ordinary thunderstorms into rotating supercells. In Texas and New Mexico, fire crews were looking at a different threat. Dry grass, powerful winds, low humidity, temperatures climbing. A landscape that had been drying for weeks was now being placed under the kind of weather that can turn a small spark into a fast-moving disaster. And farther east, rivers and creeks were rising under repeated rounds of rain. Floodwatches and warnings began appearing across parts of the Midwest, where soil already holding too much water was about to receive even more. Snow, heat, tornadoes, fire, flooding, all on the same day, all across the same country. And the most important part is this: these were not 5 separate stories. They looked separate on television. They sounded separate in local weather reports. One city heard about heat, another heard about snow, another heard about storms, another heard about fire danger. But high above the ground, where the real architecture of weather is built, all of these events were connected. They were different faces of one enormous atmospheric pattern, one wave, one continental scale machine, one invisible structure stretching across North America and forcing the atmosphere to behave like every season had arrived at once. Most people never see weather this way. We experience weather locally. We feel the heat on our skin. We hear tornado sirens in our own county. We see snow outside our own window. We watch floodwater rise on our own street. So when strange things happen far away, they feel unrelated. A blizzard in Wyoming feels like a Wyoming story. A heat wave in Boston feels like a Boston story. A tornado outbreak in Kansas feels like a Kansas story. But the atmosphere does not care about state lines. It does not divide itself into local news markets. It does not separate disasters into neat categories the way warning systems do. The atmosphere is one connected system. And on this day, that system revealed itself. The question is not simply why it snowed in the mountains or why the East Coast got hot. The question is why these extremes happened together. Why now? Why in this pattern? And why are scientists increasingly concerned that these kinds of connected extremes may be appearing more often? Because this was not just a strange weather day. It was a preview, a glimpse of how the atmosphere behaves when a giant wave in the jet stream becomes amplified, slows down, and locks different regions into different extremes at the same time. One side of the wave pulls cold air south and creates snow. Another side pushes hot air north and creates a heat dome. The boundary between them becomes a storm zone. The dry side becomes a fire zone. The wet side becomes a flood zone. And suddenly, a single weather pattern becomes many disasters. Tonight, we are going to follow that pattern. We will start on the ground, where America appeared to lose its seasons. Then we will rise into the upper atmosphere and look at the invisible giant responsible for connecting these events. After that, we will move east, into the heat dome, where the most dangerous part of the story may not be the temperature itself, but the timing. Because early season heat is different. It arrives before bodies are ready, before cities are prepared, before people take it seriously. And then, as we move through this story, we will begin to see the bigger picture. The blizzard was not random. The heat was not isolated. The tornadoes were not separate. The fires were not coincidence. They were all connected by the same atmospheric engine. And once you understand that engine, the weather map starts to look very different. What looked like chaos becomes structure. What looked like coincidence becomes physics. And what looked like one strange day becomes a warning about the kind of patterns the future may bring more often. So tonight, we begin with the day America stopped having one season and started having all of them at once. Chapter 1. The day America lost its seasons. There are some days that feel wrong before anyone explains why. You step outside, and the air does not match the calendar. The sky feels out of place. The wind carries the wrong season. The atmosphere feels like it has skipped ahead, fallen behind, or forgotten what month it is supposed to be. This was one of those days. Across America, millions of people woke up inside weather that did not seem to belong where it was. In the high country of Wyoming, spring had vanished. Snow was falling hard across mountain roads and open stretches of interstate. Wind pushed it sideways across the pavement. Visibility dropped until the road ahead looked like a fading gray tunnel. The kind of conditions people expect in January had returned in May. Drivers who had packed for spring suddenly found themselves in winter. A few hours later and hundreds of miles away, the opposite problem was building. The East Coast was getting hot, not pleasantly warm, not just sunny, hot in a way that felt early, sharp, and out of rhythm. Cities that had recently been living through mild spring weather were now preparing for temperatures that belonged deeper in summer. For people in Boston, New York, Philadelphia, Baltimore, and Washington, the danger was not just that the numbers were high. The danger was that the body had not been trained for them yet. Early heat is dangerous because it surprises people. Air conditioners may not be ready. Outdoor workers may underestimate it. Elderly people may not recognize how quickly indoor temperatures can rise. Children practicing sports may push too hard. People hear heat and think of July, but when that heat arrives in May, it can hit harder than expected. Meanwhile, in the middle of the country, the atmosphere was becoming violent. Across the plains, warm, moist air was being pulled north from the Gulf. Above it, colder and drier air was moving in. Winds were strengthening and turning with height. These are the ingredients meteorologists watch closely because when they line up correctly, storms can begin rotating. A thunderstorm is already powerful, but a rotating thunderstorm is different. It can organize itself. It can sustain itself. It can produce giant hail, destructive winds, and tornadoes capable of changing entire communities in minutes. While the plains watch the sky, the Southwest watch the ground. In parts of Texas, New Mexico, Oklahoma, and nearby regions, drought had already prepared the landscape for fire. Grass and brush were dry, soil moisture was low, winds were strengthening, humidity was falling. That combination is dangerous because fire does not need much on a day like that. A spark from equipment, a power line, a vehicle, a careless burn, a lightning strike. Under normal conditions, a small fire might be contained quickly. But under extreme fire weather, the atmosphere itself becomes part of the fire. Wind feeds it. Dry air accelerates it. Heat preconditions the fuel. Fire crews are forced to chase something that can move faster than people expect. And then there was the water. In parts of the Midwest, heavy rain threatened areas where rivers and soils were already under stress. Thunderstorms moving repeatedly over the same region can turn a normal rain event into a flood situation very quickly. The first storm wets the ground. The second storm fills the creeks. The third storm turns roads into streams. So by the time forecasters looked across the country, the map no longer looked like one season. It looked like all 4 seasons had been placed over America at the same time. Winter in the mountains, summer in the east, spring severe storms in the plains, autumn-like fire danger across dry landscapes, flooding where moisture kept returning. This is what made the day remarkable. Not that there was snow, not that there was heat, not that storms formed, not that fire danger existed. America is a large country. Extreme weather happens. The remarkable part was the simultaneity, the way these hazards appeared together, the way they overlapped in time, the way they seemed, at first, disconnected, but became more connected the farther meteorologists zoomed out. That is the part most people never see. Local forecasts are designed to protect local communities. They are important. They save lives. If you are in Wyoming, you need to know about snow and road conditions. If you are in Boston, you need to know about heat. If you are in Kansas, you need tornado warnings. If you are in Texas, you need fire alerts. But local warnings do not always explain the larger pattern. They tell you what is happening where you live. They do not always show you why it is happening across the entire continent. And on this day, the why was the real story. Because above the surface, the atmosphere was not behaving randomly. It was organized. A large trough had dug into the western part of the country, allowing colder air to dive south and helping produce snow in higher elevations. On the other side of the pattern, a powerful ridge was building over the east, helping heat expand northward. Between them, the plains became a collision zone where storms could explode. Along the dry side of the system, winds and low humidity created fire danger. Along the wet side, repeated rainfall raised flooding concerns. One pattern, many consequences. That is how the atmosphere works when it becomes amplified. Think of it like a giant bend in a river. When a river flows straight, the current moves forward cleanly. But when the river begins to twist and loop, some places get carved away while others collect sediment. The shape of the river determines what happens along its banks. The jet stream works in a similar way. When it flows smoothly, weather systems move along. But when it bends deeply, one region can be trapped under cold air while another is trapped under heat. Storms can repeatedly form along the boundaries. Dry air can be pulled into one zone. Moisture can be focused into another. The shape of the flow creates the disasters. And on this day, That shape was extreme enough to make America look like it had lost its seasons. For the people living through it, the experience was local. A driver gripping the steering wheel in Wyoming was not thinking about heat in Boston. A parent in Philadelphia checking on an elderly relative was not thinking about fire danger in Texas. A storm chaser in Kansas was not thinking about flooding in Missouri. But all of them were living under the same atmospheric pattern. Different lives, different risks, different landscapes, same system. And that is why this day matters. Because it reminds us that weather is not just what happens outside our window. It is part of a much larger machine. A machine that can connect snow and heat, fire and flood, calm mornings and violent afternoons. To understand that machine, we have to leave the surface. We have to go higher. Above the roads, above the cities, above the storms, up into the river of air that steers everything below it. Because the next part of this story begins with an invisible giant moving across North America. Chapter 2. The Invisible Giant over North America. Most of the time, the most important weather feature in your life is something you will never see. It does not look like a storm cloud. It does not flash with lightning. It does not appear on the horizon like a wall of rain. It moves high above the ground, thousands of feet over our heads, in a part of the atmosphere most people never think about. But it can decide whether your city gets heat, snow, storms, fire weather, flooding, or calm blue skies. It is the jet stream, a river of fast-moving air flowing around the planet. And on this day, that river was not flowing smoothly. It was bending, deeply, dramatically, powerfully enough to divide an entire continent into different weather worlds. To understand what happened, imagine a ribbon stretched across North America from west to east. Under normal conditions, that ribbon may wave slightly as weather systems move along it. Small bends, small dips, small rises. Enough to create day-to-day changes, but not enough to completely rearrange the country's weather. Now imagine that ribbon becoming unstable. It begins to swing north in one region and plunge south in another. The bends become larger. The movement slows. The atmosphere starts holding its shape instead of quickly moving on. That is when weather becomes dangerous. Because the jet stream is not just air moving fast. It is a boundary. On one side, colder air. On the other side, warmer air. When the jet stream bends south, it can drag cold air into places that were expecting spring. When it bends north, it can pull heat into regions that are not ready for summer. And along the boundary between those air masses, storms can become violent. This is where the idea of a Rossby wave becomes important. A Rossby wave is a large-scale wave in the atmosphere. It is one of the basic ways the planet moves heat around. These waves help transfer warm air toward the poles and cold air toward the equator. They are normal. They are natural. They are always part of the atmosphere. But sometimes they grow, they amplify. And when they amplify, their effects can become enormous. A small wave in the jet stream might bring a cold front, some rain, or a few windy days. A large amplified wave can reshape weather across a continent. That is what happened here. A deep dip in the jet stream formed over the western United States. Meteorologists call this a trough. A trough is often associated with colder air, rising motion, unsettled weather, and storm development. This trough helped bring colder conditions into the Rockies and high plains. It supported the late-season snow. It created lift in the atmosphere. It pushed energy out into the plains, where storms could form. But a trough is only one side of the wave. On the other side, the jet stream rose northward over the east. Meteorologists call that a ridge. A ridge is usually associated with sinking air, warmer temperatures, clearer skies, and heat building near the surface. That ridge helped create the East Coast heat. So the same wave that allowed snow in the west helped build heat in the east. That sounds strange only because we are used to thinking about weather locally. But at the scale of the atmosphere, it makes perfect sense. A wave has two sides. One side dips down. One side rises up. One side opens the door for cold air. One side opens the door for warm air. And if the wave becomes strong enough, the difference between those two sides can become extreme. This is why the blizzard and the heat wave were not opposites in the way people might think. They were partners. They were two outcomes of the same atmospheric shape. The western trough created one world. The eastern ridge created another. Between them, the plains became the battleground. That middle zone is where warm, moist air from the south can collide with colder air from the west. When the atmosphere is unstable and winds are strong, thunderstorms can grow rapidly. Some become supercells. Some produce giant hail. Some produce tornadoes. At the same time, the backside of the trough can drag dry air and strong winds over drought-affected land. That creates fire danger. The atmosphere is moving fast. The land is dry. Humidity collapses. Fire becomes easier to start and harder to stop. So when meteorologists looked at the map, they were not seeing random chaos. They were seeing structure, the trough, the ridge, the collision zone, the dry side, the wet side, all parts of the same wave. This is the hidden architecture behind the day America lost its seasons. And it matters because the public warning system usually breaks weather into categories. Winter storm warning, heat advisory, tornado watch, red flag warning, flood warning. Each product is useful. Each one tells people what they need to do. But each one also separates the atmosphere into pieces. The atmosphere itself is not separated. It is connected. This is why a person watching local news may hear about heat in one state and snow in another and think, that is strange. But a meteorologist looking at the upper atmosphere sees the connection immediately. The snow is under the trough. The heat is under the ridge. The storms are along the boundary. The fire danger is on the dry, windy side. The flooding is where moisture keeps repeating. Different hazards. Same wave. The most concerning part of an amplified wave is not just what it produces. It is how long it can hold. When patterns move quickly, dangerous conditions may only last a short time. A front passes. Temperatures drop. Storms move away. The atmosphere resets. But when a wave slows down, regions can remain trapped under the same conditions. Heat builds day after day. Rain falls over the same area again and again. Fire weather persists. Storm tracks repeat. Snow continues in favored terrain. This is why meteorologists pay so much attention to the speed and shape of these waves. A slow-moving, amplified pattern can turn ordinary weather into a prolonged event. And that is one of the questions scientists are studying closely. Are these patterns becoming more persistent? Are they becoming more amplified? Are they appearing in combinations that models have difficulty predicting? There is still debate. The science is complex. Not every extreme weather event can be blamed on one simple cause. But what is clear is that these large-scale waves are central to understanding simultaneous extremes. If you only look at the surface, the day looks chaotic. But if you look at the jet stream, the day becomes a map of cause and effect. Cold air here, heat there, storms in between, fire on one flank, flooding on another. The invisible giant over North America was not just passing overhead, it was shaping everything below it. And the clearest, most dangerous example of that power was building under the eastern side of the wave, where millions of people were about to experience heat that arrived too early, too fast, and too intensely for the season. That is where we go next. Into the heat dome. Chapter 3. The heat dome. Heat is easy to underestimate. Snow looks dangerous. Tornadoes look terrifying. Floodwater looks powerful. Fire looks violent. But heat often arrives quietly. No sirens at first. No dramatic wall cloud. No flames on the horizon. Just sunlight. Still air. A warm morning that becomes a hot afternoon. A room that slowly stops cooling. A sidewalk that radiates heat back into the city. A body working harder than usual without realizing how much stress it is under. That is what makes heat one of the most dangerous forms of weather. And on this day, the eastern side of the atmospheric wave was preparing to deliver heat into a region that had not yet adjusted to it. Across the East Coast, temperatures were expected to climb into levels that felt more like midsummer than spring. Cities from Washington to Baltimore, Philadelphia, New York, Hartford, and Boston were looking at a sharp warm-up. The air mass overhead was unusually warm. The ridge above the region was strengthening. Sinking air was compressing and heating the atmosphere below. This is the basic structure of a heat dome. A heat dome forms when high pressure builds over a region and acts almost like a lid. Air sinks. Clouds struggle to form. Sunshine becomes more direct and persistent. The ground warms. Buildings absorb heat. Roads and rooftops store it. Day after day, the warmth can compound. In summer, people recognize the danger more quickly. But in spring, heat is more deceptive. May still feels like a transition month. People are planning graduations, school events, outdoor work, travel, sports, and the beginning of summer routines. Many homes have not fully switched into cooling mode. Some people have not checked their air conditioners. Public cooling centers may not yet be operating at full seasonal capacity. Workers may not be on full heat protocols. The body is also not ready. Human beings can adapt to heat, but not instantly. It takes repeated exposure over days and weeks for the body to become more efficient at cooling itself. Sweat response changes. The cardiovascular system adjusts. People become better able to tolerate heat stress. But when the first major heat event arrives suddenly, that adaptation has not happened yet. That means the same temperature can be more dangerous in May than it would be later in the summer. A 95-degree day in August is dangerous. A 95-degree day in May can be more shocking. Not because the number is higher, but because people and systems are less prepared. This is why early season heat gets the attention of public health officials. The first heat event can reveal vulnerabilities quickly. Elderly people living alone, people without reliable cooling, outdoor laborers, children, athletes, people with medical conditions, people in dense urban neighborhoods where concrete and asphalt hold heat long after sunset. Cities are especially vulnerable because of the urban heat island effect. During the day, pavement, brick, steel, and rooftops absorb solar energy. At night, they release that heat slowly. Rural areas may cool down more efficiently after sunset, but cities often stay warmer. That means the body gets less relief overnight. And overnight relief matters. Heat becomes more dangerous when nights stay warm because the body does not fully recover. A person can manage one hot afternoon if they cool down overnight. But if the apartment stays hot, if the air remains heavy, if the body continues working through the night, stress accumulates. That is why a heat dome is not only about the afternoon high temperature. It is also about duration. How many hours does the heat last? How warm are the nights? How many days does the pattern hold? How early in the season does it arrive? On this day, the East was not just dealing with warmth. It was dealing with a pattern that had placed unusually hot air overhead and was allowing that air to mix down toward the surface. High above the ground, meteorologists look at temperature levels in the lower atmosphere to understand what kind of air mass is moving into place. If the air several thousand feet above the surface is unusually warm, and if the sun heats the ground enough to mix the atmosphere, that warmth can be transported down to where people live. That is why forecasters were paying close attention. The heat was not random. It was supported from above. The ridge was creating the conditions. The sinking motion was warming the air. The surface was receiving strong late spring sun. Dryness in parts of the air mass allowed temperatures to rise efficiently. And because this was the eastern face of the same wave producing snow in the west, the heat had a larger meaning. It was not just an isolated hot spell. It was part of a continental scale contrast. Cold air was being pulled south on one side. Warm air was being pushed north on the other. The atmosphere was stretching the difference between seasons across the map. That contrast is one reason the day looks so strange. While one region was fighting winter conditions, another was preparing for summer heat. But both were created by the same shape in the upper atmosphere. For people living under the ridge, the experience was simple. It felt hot. But the cause was anything but simple. It involved the jet stream, the position of the trough, the strength of the ridge, the movement of air from the south, the amount of sunshine, the dryness of the lower atmosphere, the timing of the season, the way cities trap heat, the way bodies respond before acclimation. That is why heat can be such a complicated hazard. It looks simple, but it affects everything. Transportation systems strain, power demand rises, outdoor events become risky. Hospitals prepare for heat-related illness. Schools reconsider activities. Workers slow down or face danger. People without cooling become vulnerable. And unlike storms, heat does not always create a single dramatic moment. A tornado has a path. A flood has a waterline. A fire has flames. Heat has statistics. Ambulance calls. Emergency room visits. Power usage. Indoor temperatures. Deaths that may not be fully counted until later. That makes it quieter, but not less serious. And the early timing made this event especially important, because when heat arrives before summer, it acts like a test. A test of infrastructure, a test of public awareness, a test of health systems, a test of how prepared people are for a climate pattern that may deliver stronger extremes earlier than expected. The heat dome would eventually break. Patterns always do. A cold front would arrive. Temperatures would fall. People would step outside and feel relief. But that relief would not erase the larger lesson, because the heat was only one face of the wave. The same atmospheric structure that placed millions under unusual warmth was still producing other hazards elsewhere. The snow had not disappeared from the story. The storms were still forming. Fire danger was still rising. Flood concerns were still active. The East Coast heat was not the whole event. It was the most populated face of it, the face felt by millions of people, the face that would dominate local forecasts. But to understand the full power of the pattern, we have to return to the other side of the wave. Back to the mountains. Back to the highways. Back to the place where May looked like winter. Because while the East was heating up, Wyoming was still disappearing into snow. Chapter 4. The May Blizzard. While the East Coast was preparing for heat that felt weeks ahead of schedule, another part of America was being pulled backward into winter. In Wyoming, the calendar said spring, but the sky said something else. Snow moved across the high country in thick, wind-driven sheets. Roads that had been dry or wet only hours earlier became slick, buried, and dangerous. Visibility collapsed so quickly that drivers could lose sight of the vehicle ahead of them in seconds. The horizon disappeared. The mountains vanished. The road became a narrow gray line surrounded by white. For people who do not live in this part of the country, a snowstorm in May may sound surprising. For people who know the high country, it is not impossible. The Rocky Mountains can hold on to winter long after cities farther east have moved into spring. Elevation changes everything. Air cools as it rises. Storms that produce cold rain at lower elevations can produce heavy snow just a few thousand feet higher. Mountain passes can turn dangerous even when valleys below are dealing with an entirely different kind of weather. But this event was not just a little late-season snow. This was a serious winter storm setup arriving in the middle of a broader national weather pattern that was already producing extremes in multiple regions at once. The most dramatic symbol of that was Interstate 80. I-80 is one of the most important transportation corridors in the United States. It stretches across the country, carrying commuters, families, long-haul truckers, commercial freight, fuel, food, machinery, and emergency supplies. In Wyoming, it crosses some of the most exposed, wind-prone terrain in North America. This road is famous for dangerous winter conditions. Even during the heart of winter, it can become a battleground between traffic and the atmosphere. Wind races across open terrain. Snow blows over the pavement. Ice forms quickly. Visibility can drop to almost nothing. Large trucks become vulnerable to rollovers. Drivers can become trapped between closures with nowhere to go. Now imagine that same corridor under blizzard conditions in May. A time when many travelers may not be mentally prepared for winter driving. A time when some vehicles may no longer be carrying winter supplies. A time when people may have already shifted into spring routines. That mismatch between expectation and reality is part of what makes transition season storms dangerous. In January, people expect winter. In May, they do not. And that can change behavior. A driver may leave without checking the mountain forecast. A trucker may assume the worst of winter has passed. A family crossing the state may not expect a whiteout. A delay that would feel normal in February may feel unbelievable in late spring. But the atmosphere does not care what month it is. If the ingredients are present, winter can return. And on this day, the ingredients were there. Cold air had been drawn south and downward into the western side of the atmospheric wave. A deep trough in the upper atmosphere helped create lift, instability, and colder conditions across the Rockies and nearby high terrain. Moisture moved into areas where rising terrain could squeeze it out of the air as snow. Winds strengthened. Snowfall intensified. Blowing snow reduced visibility. The result was not just snow falling from the sky. It was snow being weaponized by wind. That is the key difference. A snowstorm can slow travel. A blizzard can erase the road. Blizzard conditions are not defined by snow totals alone. They depend on visibility and wind. You can have several inches of snow and not have a blizzard. You can also have falling snow and blowing snow combining with powerful wind to create conditions far more dangerous than the accumulation number suggests. That is what made the Wyoming side of this pattern so serious. The snow did not have to pile up to historic depths to become dangerous. It only needed to fall and blow hard enough to blind drivers, cover roads, and make travel unsafe. In the mountains and foothills, some areas were expecting heavy totals. Higher elevations could receive enough snow to affect travel, backcountry conditions, livestock, power lines, and spring runoff patterns. Heavy wet snow is especially difficult because it clings to surfaces. It loads tree branches. It weighs down power lines. It can turn roads into slush and then freeze as colder air arrives. And because this was happening in May, the snow had another effect. It interrupted the normal rhythm of spring melt. In mountain regions, snowpack acts like a water bank. Snow accumulates in winter, then melts gradually through spring and early summer, feeding rivers, reservoirs, irrigation systems, and ecosystems downstream. When a late-season storm drops heavy wet snow onto an already changing snowpack, it can temporarily reset the surface. It can delay melt in some places, add water to the system, and then create a stronger melt pulse later if warm weather returns quickly. That means a May snowstorm is not only a travel problem, it can become part of a hydrology story. What falls as snow in the mountains today may become stream flow days or weeks later. If the pattern flips back to warmth, that added snow can melt quickly. If rain falls on top of snow, runoff can accelerate. If rivers are already running high, a late snow event can become part of a future flood concern. This is how one weather event can echo beyond its immediate impact. But the most important reason this snow matters in the larger story is not simply that it happened. It is where it happened in the wave. The Wyoming blizzard was not isolated from the East Coast heat. It was the opposite face of the same atmospheric structure. The deep trough over the west allowed colder air to dig southward. The ridge over the east allowed heat to surge northward. These features were connected like two sides of a giant atmospheric seesaw. When one side dipped, the other rose. This is why the day looked so unnatural from the ground. One side of the country was being pushed back toward winter. The other was being pulled forward into summer. The same wave created both distortions. For someone standing in Wyoming, it felt like winter had returned. For someone standing in Boston, it felt like summer had arrived early. But from above, it was one shape, one bend in the jet stream, one amplified pattern, one giant atmospheric machine distributing extremes across the map. And this is what makes amplified patterns so powerful. They do not produce one type of weather everywhere. They produce contrast, cold next to heat, dry next to wet, calm next to violent, snow in one region and record heat in another. That contrast can be shocking because humans experience weather through place and time. We expect seasons to progress in an orderly way. Spring should slowly become summer. Winter should retreat. Heat should build later. Snow should become rarer. But the atmosphere is not a straight line. It is a moving, bending, rotating fluid system. And sometimes in the transition months, that system can bring winter and summer into the same national weather map. That is exactly what happened here. The Wyoming snow became the visual proof. It gave people something they could understand immediately. a truck on a whiteout highway, a road closure, snow blowing sideways across an interstate, a mountain pass buried beneath conditions that felt completely out of season. Those images are powerful because they show the atmosphere's contradiction, but they also risk misleading people. Because the blizzard was not the whole story, it was the cold face of the wave, and on the warm side of that same wave, something else was happening. Energy was moving out of the Rockies and into the plains. The same trough that helped generate snow in Wyoming was also preparing the atmosphere farther east for severe storms. As cold air moved in above the ground and warm, moist air surged north near the surface, the central United States became unstable. Winds strengthened and changed direction with height. Boundaries sharpened. Storms began to find the ingredients they needed. The snowstorm was the warning sign. The atmosphere had become highly amplified. And when an amplified western trough begins ejecting energy into warm, moist air across the plains, the next hazard is not winter. It is violence. Rotating storms, giant hail, damaging winds, tornadoes. The same wave that buried Wyoming in snow was about to awaken Tornado Alley. Chapter 5. Tornado Alley Awakens. In the Central Plains, severe weather does not begin when the first tornado touches the ground. It begins hours earlier, sometimes before sunrise. It begins with forecasters studying maps, wind profiles, moisture levels, instability, boundaries left behind by earlier storms, satellite images showing where clouds are clearing and where sunlight is heating the ground, radar screens showing small areas of development that may become something much larger later in the day. To most people, the morning may look ordinary, maybe humid, maybe cloudy, maybe strangely warm and windy. But to meteorologists, storm chasers, emergency managers, and anyone who has lived through a dangerous plains outbreak, the atmosphere can feel loaded before the first warning is issued. This was that kind of setup. Across parts of Kansas, Nebraska, Missouri, and surrounding areas, the ingredients for severe thunderstorms were moving into place. Warm, moist air was being pulled northward. Above it, colder air was moving in from the west. Winds near the surface were blowing from one direction, while winds higher up were moving faster and from another direction. That changing wind with height is called wind shear, and wind shear is one of the most important ingredients in tornadic storms. A normal thunderstorm rises and collapses. Warm air goes up, rain-cooled air comes down, and the storm may weaken as its own outflow cuts off its supply of fuel. But with the right wind shear, a thunderstorm can organize. The rising air can begin rotating. The storm can separate its inflow from its outflow. Instead of choking itself, it can breathe. That is when a storm can become a supercell. And supercells are the storms meteorologists watch with the most concern. They can produce giant hail. They can generate destructive winds. They can drop tornadoes. They can persist for hours. They can move across county after county, carrying danger over long distances. On this day, the plains were positioned in the dangerous middle zone of the larger atmospheric wave. To the west, colder air and upper-level energy were moving out of the trough. To the south, warm moisture was being transported north. To the east, the ridge was helping pull that warmth and humidity into place. The plains became the collision zone. And in weather, collision zones are where quiet afternoons can turn violent. The first thing forecasters often watch for on a day like this is instability. Instability is the atmosphere's stored energy. It describes how strongly warm air near the ground wants to rise into colder air above. The greater the temperature difference between the surface and the middle atmosphere, the more explosive storms can become if they manage to form. But instability alone is not enough. A hot, humid day can remain storm-free if warm air is trapped beneath a cap, a layer of warmer air above the surface that prevents storms from rising. This cap can suppress development for hours, but if the cap breaks, the release can be sudden. Storms may erupt quickly. One moment, the sky is building. The next, radar shows rapidly strengthening cells. In the plains, this waiting game can be tense. Too strong of a cap, and storms never fully form. Too weak of a cap, and storms form too early, become messy, and interfere with each other. But if storms form at the right time, in the right place, with strong instability and wind shear, the atmosphere can produce dangerous, isolated supercells. That was the concern. As the day moved forward, boundaries became critical. A dry line, a cold front, a warm front, outflow from earlier storms. Each boundary acts like a trigger, forcing air upward and allowing storms to develop. In a setup like this, small differences matter. A boundary 50 miles north or south can change which towns are at greatest risk. A cloudy morning can reduce heating. A pocket of sunshine can increase instability. Earlier storms can either stabilize an area or create new zones of rotation where later storms become stronger. This is why severe weather forecasting is both science and constant observation. The broad pattern may be visible days in advance, but the exact locations of the strongest storms can depend on details that only become clear hours before the event. For communities in the risk zone, this creates a difficult kind of uncertainty. People know danger is possible, but they may not know whether the storm will come directly toward them. They wait. They check radar. They listen for watches. They watch the sky darken. And then, sometimes the atmosphere begins to move. The first storms form along the boundary. They rise rapidly. Their tops push higher into the atmosphere. Radar begins to show rotation. Storm chasers reposition. Local news cuts into programming. Phones begin vibrating with alerts. A severe thunderstorm warning appears. Then another. Then a tornado watch. Then, in some places, the warning everyone fears. Tornado warning. Take shelter now. For people who have never experienced that moment, the words may sound routine. For people inside the warning polygon, they are not routine. They change the room. A family moves into a basement. A school moves students away from windows. A hospital prepares for power disruptions. A factory stops work. A driver looks for shelter and realizes there may be none. A town listens for sirens and watches the sky turn the wrong color. Tornadoes are terrifying because they are both powerful and personal. A heat wave affects a region. A blizzard affects a corridor. A flood affects low-lying areas. But a tornado can destroy one street and leave the next one standing. Its path can be narrow, violent, and almost unbelievable. One house gone, another damaged, another untouched. That randomness is part of the fear. But in the atmosphere, tornadoes are not random. They emerge from structure, instability, moisture, lift, wind shear, rotation, boundaries, storm-scale interactions. And all of those ingredients were being shaped by the larger wave. The western trough was sending energy into the plains. The surface low and boundaries helped organize the storm environment. Warm, moist air from the south supplied fuel. Stronger winds aloft created shear. The contrast between the cold side and warm side of the system sharpened the setup. In other words, the tornado threat was not separate from the Wyoming snow or the East Coast heat. It was the central face of the same atmospheric pattern. The trough created snow where the air was cold enough. The ridge created heat where sinking air dominated. Between them, the plains became the storm factory. This is how one wave can produce wildly different hazards. Where the air rises over cold terrain, it snows. Where air sinks under high pressure, it heats. Where air masses collide, storms explode. Where dry air and wind overlap with drought, fires become possible. The same system expresses itself differently depending on the local ingredients beneath it. For the plains, those ingredients favored severe weather. And severe weather in this region has a long memory. Towns across Kansas, Nebraska, Oklahoma, Missouri, and Iowa know what these days can become. They know the language of warnings. They know the difference between a watch and a warning. They know that the sky can change quickly. They know that a storm visible on the horizon can become life-threatening before there is time to think clearly. That is why preparation matters before the first siren. Shelter plans, weather radios, charged phones, shoes near the safe place, helmets for children if available, a plan for pets, a plan for nighttime storms. Because when the atmosphere enters this kind of mode, minutes matter. The outbreak risk also carried another danger: hail. Large hail is sometimes treated as secondary compared to tornadoes, but it can be destructive and deadly. Hailstones falling from supercells can break windows, destroy crops, injure livestock, damage roofs, and shatter windshields. When hail reaches baseball or softball size, being caught outside can become life-threatening. Hail forms inside powerful storm updrafts. Water droplets are carried above the freezing level, freeze, fall, and then get lifted again, adding layers of ice. The stronger the updraft, the larger the hailstone can grow before gravity finally wins. A day with strong instability and steep temperature changes above the ground can support very large hail. That was part of the concern across the plains. So the threat was not one-dimensional. Tornadoes, giant hail, damaging winds, flooding rainfall, all possible from the same storm environment. And as storms moved east, another hazard began to grow: training rain. When storms repeatedly move over the same area, flash flooding can develop quickly. Roads flood, creeks rise, low water crossings become deadly. Urban drainage systems back up. What begins as severe weather can turn into a water emergency after sunset. This is why the plains outbreak was not only about dramatic tornado images, it was part of a broader multi-hazard day. A day where the same wave produced too many different threats for any single headline to capture. And while the plains watched the sky, another region watched the horizon. Because on the dry side of the same atmospheric system, the threat was not rotating clouds. It was flame. The southern high plains had heat, wind, drought, and fuel. And that combination can turn one spark into a race against time. Chapter 6. The Fire Front. Fire weather begins before there is a fire. It begins in the soil, in the grass, in the brush, in the weeks without meaningful rain, in the afternoons when humidity drops and the wind keeps pulling moisture out of the land. By the time an extreme fire weather day arrives, the landscape has often been prepared for it long before the first spark. That is what made the southern high plains so dangerous in this pattern. The same atmospheric wave that brought snow to Wyoming and tornado ingredients to the plains was also pushing dry, powerful winds across drought-stressed land farther south and west. This was the fire face of the wave, and it may have been the most conditional danger of all. Because unlike a blizzard, a heat wave, or a storm outbreak, a fire weather setup does not always guarantee a disaster will happen. The atmosphere can create the conditions. The land can provide the fuel, but something still has to ignite. That is the terrifying uncertainty. On extreme fire weather days, the difference between a quiet afternoon and a major disaster can be a single spark. A piece of equipment striking rock, a vehicle dragging a chain, a power line fault, a lightning strike, a burn pile that gets out of control, a cigarette tossed into dry grass. One mistake, one accident, one unlucky moment, and the entire character of the day changes. Across parts of Texas, New Mexico, Oklahoma, and nearby regions, the land had been drying. Grasses were cured. Brush was receptive. Soil moisture was low. The surface had been losing water under persistent warmth and wind. Then the larger weather pattern added the final ingredients. Strong winds, very low humidity. Hot temperatures, dry air descending from higher terrain. This combination is dangerous because it attacks fire control from every direction. Low humidity dries fuels even more. Hot air raises fuel temperatures closer to ignition. Strong winds push flames forward, carry embers ahead of the main fire, and make it harder for crews to hold containment lines. Wind can also shift suddenly, turning a flank into a fire front and putting firefighters in danger. A grass fire under calm conditions may move slowly enough for crews to attack directly. A grass fire under extreme wind can outrun vehicles. That is why fire weather warnings matter even before smoke appears. They are not predictions that a fire already exists. They are warnings that if a fire starts, it may behave aggressively. The southern high plains are especially vulnerable to fast-moving fires because of the landscape. Open grasslands, long distances, strong winds, limited natural barriers, rural roads, scattered homes, ranches, farms, and small communities. In this environment, a fire can move quickly across open country, threatening livestock, homes, equipment, power infrastructure, and entire towns before resources can arrive from far away. And unlike a city fire, a wind-driven grass fire does not always provide much warning. Smoke appears on the horizon, then the wind carries it closer, then emergency alerts go out, then roads may close, then evacuation decisions must be made quickly. The speed can be shocking. This is why experienced fire managers watch weather days like this with such concern. They know that the atmosphere has created a narrow window where ignition could become explosive. The key mechanism on this day was downslope drying. When air descends from higher elevations, it compresses and warms. As the temperature rises, relative humidity falls. The air may not lose moisture in an absolute sense, but because warmer air can hold more water vapor, the relative humidity drops. That makes the air feel and behave much drier. In the southern Rockies and high plains, this process can create extremely dry surface conditions. Add strong winds from the larger storm system, and the result is a fire environment where fuels can ignite easily and flames can spread fast. This connects directly back to the larger wave. The Western Trough was not only creating cold and snow in one location, its circulation was also helping drive wind across the dry side of the system. Air moving around the trough descended into lower elevations, warmed, dried, and accelerated. So the same atmospheric structure that created winter conditions in the mountains created fire conditions on the plains below and downstream. That is the strange power of an amplified wave. It does not produce the same hazard everywhere. It produces the hazard each landscape is ready to express. In the cold mountains, it produced snow. In the warm, moist plains, it produced severe storms. In the dry, wind-exposed high plains, it produced fire weather. The atmosphere supplied the motion. The land supplied the vulnerability. And drought was the quiet partner in the background. Drought changes everything about fire risk. When soil moisture is low, vegetation dries faster. Grasses cure earlier. Shrubs lose moisture. Dead fuels become more receptive. Even living vegetation can begin behaving more like fuel if the dryness persists long enough. This means fire danger is not only about the weather on the day of the event. It is about the weeks and months before it. A windy day after a wet spring is one thing. A windy day after a long dry stretch is something else entirely. On this day, the atmosphere arrived over a landscape that had already been prepared. That is why the phrase loaded gun fits fire weather so well. The drought loads the gun, the wind pulls the trigger, and the spark decides whether the shot is fired. In many regions, fire weather also creates difficult communication challenges. People may see a warning and think nothing is happening because there is no fire yet. The sky may be blue, the sun may be shining, life may seem normal, but the danger is conditional. It is potential energy waiting for ignition. That can make warnings harder to take seriously. A tornado warning tells you a storm is happening now. A flood warning tells you water is rising. A blizzard warning tells you conditions are already dangerous. A red flag warning tells you the environment is ready. And because the disaster has not yet started, prevention becomes the most important action. Do not burn. Do not drag chains. Avoid activities that create sparks. Secure trailers. Be careful with equipment. Report smoke quickly. Have an evacuation plan if you live in a vulnerable area. Small actions matter because on extreme fire weather days, prevention is easier than control. Once a wind-driven fire begins, the scale can change rapidly. History has shown this again and again. Some of the most destructive fires in modern American history were not simply the result of dry land. They were the result of dry land meeting wind. Powerful winds transformed manageable ignitions into fast-moving disasters. Homes burned not because flames slowly crept toward them, but because embers flew ahead, ignited spot fires, and overwhelmed response systems. That is the nightmare scenario in fire weather. Not just a line of flame, a storm of embers. Wind carrying fire across roads, fields, and fire breaks. New ignitions appearing ahead of the main front. Crews forced to defend lives and evacuations rather than directly contain the fire. This is why the Southern High Plains fire setup belonged in the same story as the blizzard, the heat dome, and the tornado outbreak. It was another expression of the same atmospheric imbalance. The country was not just experiencing multiple hazards, it was experiencing multiple vulnerabilities being activated at once. Cold terrain received snow, urban corridors received heat, storm country received severe weather, drought country received fire danger, and wet basins received flooding risk. This is the deeper meaning of a multi-hazard wave. It finds the weak points. It presses on each region differently. It turns geography into destiny. The same pressure pattern that creates one hazard in one place creates another hazard somewhere else. That is why focusing only on individual disasters can miss the larger truth. The fire front was not separate. It was connected, and it showed how drought can transform weather into danger. Without dry fuels, the wind would still be strong. Without wind, the dry fuels would still be concerning. But together, they created a day where one ignition could become a major event. That is how compound risk works. It is not one factor. It is the overlap. Drought plus wind. Heat plus early season timing. Moisture plus instability. Cold air plus mountain lift. Rain plus saturated ground. Every region had its own equation, and the atmosphere was solving all of them at once. By this point in the story, 4 faces of the wave were visible. The heat dome in the east, the blizzard in the west, the tornado threat in the plains, the fire danger across the dry southern high plains. But there was still another face of the system, a quieter one that does not spin like a tornado or glow like a fire. It simply rises. In rivers, in creeks, in streets, in basements. The same pattern that pulled moisture north into the severe weather zone was also setting the stage for flooding. And that is where the next part of the story takes us, to the water side of the wave. Chapter 7. The water side of the wave. Not every disaster announces itself with wind. Some arrive quietly. A dark sky, a steady rain, a roadside ditch filling faster than expected, a creek rising inch by inch until the bank disappears. Water spreading across a low road that people have driven 1,000 times before. Flooding is one of the most underestimated hazards in weather because it often begins slowly. People watch rainfall and assume they understand it. They see water on a road and think they can cross it. They look at a stream and believe it will stop rising soon. But floodwater does not need drama to become deadly. It only needs time, gravity, and enough rain falling over the wrong place. On this day, while tornadoes threatened the plains and fire danger spread across the dry side of the system, the wet side of the wave was beginning to reveal itself. Across parts of the Midwest, especially areas already dealing with saturated ground and swollen rivers, repeated rounds of thunderstorms created a different kind of danger. Not the sudden violence of a tornado, not the visible wall of a wildfire, but the slow, relentless pressure of water arriving faster than the land could absorb it. This is the flood face of the wave. And like the snow, the heat, the tornadoes, and the fire weather, it was connected to the same atmospheric machine. The setup began with moisture. Warm, humid air was being pulled northward from the Gulf of Mexico. That moisture did not move randomly. It was transported by the broader circulation around the same pattern, driving the other extremes. The ridge to the east helped draw warm air north. The trough to the west provided lift and storm energy. Between them, a corridor of moisture stretched into the central United States. To a meteorologist, that corridor matters. Moisture is storm fuel, but it is also flood fuel. When humid air is lifted, the water vapor inside it condenses into clouds and precipitation. If storms move quickly, a region may receive heavy rain and then recover, but if the atmosphere keeps sending storms over the same area, rainfall begins to stack. This is called training. The name comes from the image of train cars moving along the same track. One storm passes, then another follows the same path, then another. Each storm may be manageable on its own, but together they can overwhelm the landscape. That is how flash flooding often happens, not because one drop of rain is unusual, but because too many drops fall in the same place, too quickly, for too long. On this day, parts of the Midwest were positioned near the zone where storms could repeatedly develop and move across similar areas. Boundaries in the atmosphere acted like rails, guiding storms over the same corridor. Moisture kept feeding into the region. Rainfall rates increased under stronger cells. Streams began responding, and the land already had a problem. It was not empty. It was not dry. In many places, the ground had already absorbed previous rainfall. When soil is dry, it can take in more water, at least for a while. But when soil is saturated, its ability to absorb new rain drops sharply. Water that might have soaked into the ground instead runs off into ditches, creeks, streams, and rivers. That means the same amount of rainfall can have very different effects depending on what happened before the storm arrived. A 2-inch rainfall after weeks of dry weather may create puddles. A 2-inch rainfall on saturated ground can create flash flooding. This is why flood risk is often a story of memory. The land remembers yesterday's rain. Rivers remember last week's storms. Soils remember the season. And when the next event arrives, the previous ones are still there, hidden in the ground and flowing through the waterways. That is what makes flooding different from many other weather hazards. It is not only about what falls from the sky. It is about what the land can handle when it gets there. For people in flood-prone areas, the danger can escalate quickly. A road that looks passable may be undermined beneath the surface. A small creek can rise over its banks in minutes. Urban drainage systems can clog or overload. Water can enter basements, parking lots, underpasses, and low-lying neighborhoods before people fully understand what is happening. And floodwater is deceptive. 6 inches of moving water can knock a person down. A foot of water can move many vehicles. 2 feet can carry away larger vehicles. Yet every year, people attempt to cross flooded roads because they underestimate the power of moving water. The road may still be there, or it may not. The surface may look shallow, or the pavement may have been washed out underneath. In darkness, the danger becomes even worse. Many flash flood deaths happen at night when people cannot judge depth, speed, or whether the road remains intact. That is why flood warnings matter. They are not background noise. They are instructions to stop trusting your eyes and start trusting the warning. But in a multi-hazard day, flooding can be overshadowed. Tornadoes get attention because they are dramatic. Fire weather gets attention because smoke and flames are visual. Heat gets attention because millions feel it. Snow gets attention because it looks strange in May. Flooding can be quieter, until it is not. Until a creek becomes a river. Until water crosses a road. Until a family wakes up to water entering the house. Until emergency crews are called to rescue someone who thought they could make it through. The flood threat in this pattern was another reminder that the atmosphere was not producing one disaster. It was distributing risk differently across regions. Where the air was cold enough and terrain forced it upward, snow fell. Where air sank beneath high pressure, heat built. Where warm, moist air collided with stronger winds and instability, storms rotated. Where dry air and wind crossed drought land, fire danger rose. Where moisture repeatedly lifted over the same areas, flooding became possible. Same wave, different consequences. The water side of the wave also helps explain why these patterns can become so costly. Flooding affects roads, bridges, farms, homes, water systems, and emergency services. It can close transportation routes and damage infrastructure. It can ruin crops before the growing season fully develops. It can contaminate drinking water and overwhelm wastewater systems. It can create long recovery periods after the rain has stopped. And unlike a tornado, which may strike a narrow path, flooding can spread through entire basins. A storm may fall in one county, but the water can travel downstream into another. Rivers connect regions the same way the atmosphere does. What falls upstream becomes someone else's flood later. That is why the water story cannot be separated from the broader pattern. The moisture feeding the storms was part of the same circulation that supported the heat dome and the severe weather risk. The trough provided the lift. The ridge helped maintain the warm, moist flow. Boundaries focused rainfall. Saturated soils increased vulnerability. This was not random rain. It was the wet expression of the same continental setup. By now, the full map of the day had become clear. 5 hazards, 5 faces, 1 wave. But this raises a deeper question. Why did the wave produce such intense consequences? Weather patterns have always existed. Rossby waves have always existed. Troughs and ridges are normal parts of the atmosphere. The jet stream has always bent and shifted. America has always had snow, heat, tornadoes, fire, and floods. So why did this day feel so loaded? Why did the atmosphere seem ready to produce so many different extremes at the same time? The answer is that the wave was not acting on an empty background. It was moving over a country already prepared for extremes. Dry land in some places, saturated basins in others, warm oceans feeding moisture, cities vulnerable to early heat, drought-cured fuels ready to burn, a climate system holding more energy and more moisture than it used to. The wave was the trigger, but the background conditions were the gunpowder. And to understand why the day became so dangerous, we have to look beneath the weather itself. We have to look at what had been building for weeks, months, and years before the first warning was ever issued. Chapter 8. The Loaded Background. Extreme weather rarely begins on the day it appears. The warning may be issued that morning. The storm may arrive that afternoon. The heat may peak the next day. The fire may start with one spark. The floodwater may rise in a few hours. But the conditions that make those events dangerous are often built long before anyone sees the first headline. This is the hidden part of weather disasters. The background, the slow preparation, the weeks of dryness before the fire, the repeated rain before the flood, the early warmth before the heat wave, the ocean temperatures that feed moisture into storms, the snowpack conditions that determine runoff, the urban surfaces that store heat. By the time the atmosphere produces a major event, the land beneath it has already been shaped by everything that came before. On this day, the wave was powerful, but it did not act alone. It moved across a landscape already full of vulnerabilities. That is why the phrase loaded background matters. The wave was the trigger, but the country had already been prepared. Start with drought. Drought is not always dramatic at first. It does not arrive like a tornado. It does not move like a flood. It creeps. A dry week becomes a dry month. Soil moisture declines. Vegetation loses water. Streams run lower. Farmers notice stress in fields. Fire managers watch fuel levels change. Reservoir managers study inflows. Grasslands begin to cure. Then one day a strong wind event arrives, and suddenly the drought becomes visible as fire danger. That is what happened on the dry side of the wave. The atmosphere brought wind and low humidity, but the land provided the fuel. Without dry grass and brush, the fire threat would have been less severe. Without wind, the drought might have remained a quiet background concern. But together, drought and wind formed a dangerous overlap. This is how compound risk works. It is rarely one factor. It is the combination. Drought plus wind. Heat plus early season timing. Storms plus saturated ground. Moisture plus instability. Snow plus mountain terrain. Each hazard becomes more dangerous when the background conditions are already tilted in its favor. So while the weather map showed one wave, the impact map showed many forms of vulnerability. In the east, the vulnerability was early heat. The human body adapts to heat gradually. Cities prepare gradually. Public messaging ramps up gradually. But when a heat dome arrives early, it can beat that preparation. People have not adjusted. Cooling systems may not be ready. Outdoor workers may not yet be following full summer heat routines. Schools and sports programs may not be thinking like it is mid-July. That makes early heat more dangerous than the number alone suggests. The thermometer tells one part of the story. The calendar tells another. A hot day in late summer is serious. A hot day before summer begins can be more disruptive because it catches people in systems between seasons. This is another form of loaded background. Not drought, not fuel, but lack of acclimation. The atmosphere delivered heat into a population that was not fully prepared for it. In the Midwest, the vulnerability was water. If soils had been dry, repeated thunderstorms might still have caused problems, but the flood risk would have been lower. But where the ground was already saturated, new rainfall had fewer places to go. More water ran off. Creeks responded faster. Rivers rose higher. Flood disasters often depend on this memory effect. The atmosphere may deliver the rain in one day, but the land's response is shaped by previous days and weeks. Again, the event is not only the event, it is the event plus the background. In the plains, the vulnerability came from atmospheric ingredients stacked together. Moisture from the south, instability from warm surface air and colder air above, wind shear from changing winds with height, lift from boundaries and the approaching trough. Each ingredient matters. Remove one and the outbreak may weaken. Combine them correctly and storms can become dangerous. Here, the background was not only land conditions, it was the air mass itself. The atmosphere had prepared a volatile environment, and the wave supplied the trigger. This is why meteorologists often speak in ingredients. Severe weather is like a recipe. Heat alone does not make a tornado. Moisture alone does not make a tornado. Wind shear alone does not make a tornado. But combine them in the right way, at the right time, under the right forcing, and the result can be violent. The larger question is why these loaded backgrounds appear to be overlapping more often. This is where the science becomes more important than the spectacle. A warmer atmosphere can hold more water vapor. That means when storms develop, they may have access to more moisture. Not every storm becomes extreme, and not every rain event becomes a flood, but the potential for heavier rainfall increases when the atmosphere is carrying more water. At the same time, warming can intensify heat extremes. A heat dome forming in a warmer background climate starts from a higher baseline. The same ridge that would have produced a hot day decades ago may now produce a hotter one. A few degrees may not sound like much, but near human health thresholds, crop stress thresholds, and energy demand thresholds, a few degrees can decide whether an event becomes dangerous. Drought and heat also reinforce each other. Dry soil reduces evaporation. When there is less moisture available at the surface, more of the sun's energy goes into heating the air instead of evaporating water. That can make heat waves hotter. Hotter air dries soils further. Drier soils then support even more heating. This feedback can become powerful. It is one reason drought regions can heat so aggressively under high pressure. The land and atmosphere begin working together. On the fire side, warming and drying can lengthen the period when fuels are receptive. Fire seasons can begin earlier, last longer, and include more dangerous wind events overlapping with dry vegetation. Again, the wind does not have to be unprecedented. The temperature does not have to be unprecedented. The disaster risk can come from the overlap. That is the central idea. Overlap. A single extreme can be damaging, but simultaneous extremes strain systems in a different way. Emergency managers cannot focus on one hazard. Forecast offices must communicate multiple risks. Transportation systems are affected in different regions for different reasons. Hospitals face heat concerns while storm zones prepare for injuries. Fire crews stand ready while flood crews monitor rivers. Agriculture faces too much water in one place and not enough in another. This is why the day mattered beyond the meteorology. It exposed the challenge of compound extremes. A world where one hazard at a time is no longer the only planning assumption. A blizzard can disrupt freight in the west while heat strains power systems in the east. Severe storms can damage crops in the plains while fire weather threatens ranch land in the southwest. Flooding can close roads and delay response at the same time storms create new emergencies. Each region experiences its own crisis, but the national system experiences all of them together. That is where resilience gets tested. Weather forecasts are very good at telling people what hazard is coming. But compound patterns raise a harder question. How do we prepare when several hazards happen at once in different places for connected reasons? The atmosphere is not waiting for our systems to catch up. It simply behaves according to physics. And the physics are clear enough to understand the pattern. A large wave amplified across the continent. The trough produced cold, lift, wind, and storm energy. The ridge produced heat and sinking air. The flow between them transported moisture. Dry regions burned with risk. Wet regions flooded with concern. Mountain regions snowed. Cities heated. Plain storms rotated. But the damage potential came from the background. The prepared land. The vulnerable bodies. The saturated soils. The dry fuels. The warm air. The stored moisture. That is the loaded background. And it is one reason scientists are paying attention to days like this. Not because every individual event is unprecedented, but because the combinations are becoming harder to ignore. The atmosphere has always produced extremes. The question now is whether it is producing them together more often, with more intensity, and earlier in the season than many systems were designed to handle. That question leads us into the scientific warning behind the entire story. Because the most important part of this day may not be what happened on the ground. It may be what the pattern reveals about the future. Chapter 9. The warning scientists can't ignore. Scientists are careful people. They do not usually speak like headlines. They use probabilities, ranges, confidence levels, uncertainty, historical comparisons, model limitations. When a scientist says something is concerning, they usually mean they have looked at the data long enough to know the pattern deserves attention. And when multiple fields of science begin pointing toward the same type of risk, the warning becomes harder to dismiss. That is what makes this weather pattern important. The day itself was dramatic. Snow in one region, heat in another, tornado risk in the plains, fire danger across dry land, flooding concerns where moisture kept returning. But the bigger warning is not simply that these events happened. The warning is that they happened together. This is the phrase that matters: concurrent extremes. Concurrent extremes are multiple extreme events occurring at the same time, often in different regions, sometimes connected by the same large-scale atmospheric pattern. A heat wave by itself is one problem. A drought by itself is one problem. A flood by itself is one problem. A tornado outbreak by itself is one problem. A fire weather emergency by itself is one problem. But when several happen at once, the risk changes. The pressure on communication systems increases. Emergency resources are stretched. Supply chains are disrupted in more than one region. Agriculture can be hit from different directions. Public health systems can face multiple stressors. Insurance losses can expand. Infrastructure can be tested beyond the assumptions it was built under. This is why scientists do not only study individual disasters, they study patterns. And one of the most important patterns is the behavior of large atmospheric waves. Rossby waves are normal parts of the climate system. They help move heat around the planet. They shape the storm tracks. They influence the location of ridges and troughs. Without them, mid-latitude weather would look completely different. But when these waves become highly amplified and slow-moving, they can create persistent extremes. A ridge that sits too long can create a heat dome. A trough that digs deeply can create storms, cold outbreaks, and heavy precipitation. A stalled boundary can create flooding. A dry, windy flank can create fire danger. If the wave pattern extends across a continent or even across the hemisphere, different regions can experience different extremes at the same time. That is the scientific concern. not that waves exist, but that certain wave configurations may increase the risk of simultaneous extremes. Researchers have studied cases where planetary wave patterns were linked to major heat events across multiple agricultural regions. These patterns matter because they can synchronize risk. Instead of one breadbasket having a bad year while another compensates, multiple regions can experience stress together. That has implications far beyond weather: food prices, crop yields, water demand, energy systems, public health, migration, disaster response, international trade. The atmosphere may be invisible, but its consequences are not. This is where the story becomes larger than America. The same type of wave behavior that can produce a heat dome in one region and storms in another can also create simultaneous extremes across continents. A stalled ridge over one agricultural region, a flood pattern over another, drought in one area, heat in another. These combinations are exactly the kind of risk scientists are trying to understand more clearly. And the uncomfortable question is whether climate models have fully captured how often these patterns occur. Models are essential. They are among the most powerful tools humans have for understanding the climate system. They simulate oceans, atmosphere, land, ice, radiation, chemistry, and countless interactions between them. They help forecast future risks and guide planning. But models are not perfect. They can have biases. One possible issue researchers continue to examine is whether some models represent the jet stream and large-scale wave patterns too smoothly. If a model makes the atmosphere too zonal, meaning too west to east and not wavy enough, it may underestimate the frequency or intensity of amplified wave events. If it underestimates those patterns, it may also underestimate concurrent extremes. That matters because societies plan using projections. Cities design heat plans. Farmers choose crops. Water managers plan reservoirs. Governments prepare infrastructure. Insurance systems price risk. If the models are underestimating certain combinations of extremes, then the real world may be moving faster than the planning assumptions. This does not mean every dramatic weather day is proof of model failure. It does not mean the science is broken. It means the atmosphere is complex and certain behaviors are difficult to simulate perfectly. The honest scientific position is not panic. It is attention. Watch the patterns. Compare observations to projections. Improve models. Study the wave behavior. Understand the conditions that make extremes overlap. And communicate those risks more clearly before they become disasters. That last part may be the hardest, because the public is usually warned hazard by hazard. Heat advisory, winter storm warning, tornado watch, red flag warning, flood warning. Each warning is necessary. Each one protects people. But when the atmosphere is producing several hazards from one connected pattern, the public may never hear the whole story. A person in Boston hears about heat. A driver in Wyoming hears about snow. A farmer in Kansas hears about tornadoes. A rancher in Texas hears about fire danger. A family in Missouri hears about flooding. All of them receive useful information. But few are told that these events are connected. Few are shown the shape of the wave. Few understand that the same atmospheric pattern is pressing different parts of the country in different ways. This is not a failure of forecasters. Local weather offices are doing the job they are built to do: protect their regions. Their mission is immediate public safety. They must communicate clearly and quickly to the people in harm's way. But the atmosphere is becoming a systems problem. And systems problems require systems thinking. That means helping audiences understand not only what is happening locally, but how their local event fits inside the larger pattern. This matters because people prepare differently when they understand connection. A heat wave no longer feels like just a hot day. It becomes one sign of a larger atmospheric configuration. A snowstorm in May no longer feels like a random oddity. It becomes the cold side of the same wave. A tornado outbreak no longer feels isolated. It becomes the collision zone between air masses organized by the larger pattern. Fire danger no longer feels like only a local dryness problem. It becomes drought plus wind plus wave dynamics. Flooding no longer feels like just rain. It becomes moisture transport, saturated land, and repeated storm tracks. That kind of understanding does not replace warnings. It strengthens them. Because when people understand why a pattern is dangerous, they may take the individual warnings more seriously. The scientific warning is not that every day will look like this. It will not. Most days will still be ordinary. Weather will still vary. Some forecasts will underperform. Some patterns will weaken. Some risks will not verify. The atmosphere will always contain uncertainty. But the warning is that the atmosphere is capable of producing connected extremes, and the background climate may be increasing the odds, intensity, or impact of some of those combinations. That is enough to matter. It matters for cities that need better heat planning. It matters for rural communities facing fire and storm risks. It matters for transportation corridors crossing mountain terrain. It matters for agriculture, where too much water, not enough water, heat, hail, and wind can strike in the same season. It matters for emergency management because simultaneous hazards can stretch attention and resources. It matters for the way weather stories are told. And it matters for viewers watching events unfold who want to understand whether these disasters are random or connected. The answer is that some are connected, not by mystery, not by conspiracy, not by hidden forces, but by physics, by waves in the jet stream, by heat and moisture, by land conditions, by pressure systems, by the way the atmosphere moves energy around a rotating planet. That is the real warning. The explanation is not hidden. It is visible in the maps. It is visible in the warnings. It is visible in the way extremes appear together when the pattern amplifies. And once you see that, the weather becomes harder to ignore. Because the next time a local forecast mentions unusual heat, or late snow, or severe storms, or fire weather, the bigger question becomes obvious. What is the wave doing? Where is the trough? Where is the ridge? Where is the moisture moving? Where is the land already vulnerable? Those questions turn weather from a daily update into a system you can read. And on this day, the system was sending a message. Not that the world had ended. Not that the atmosphere was broken beyond understanding. But that the patterns capable of producing compound extremes are real, powerful, and worth watching closely. The wave would eventually move. The heat would ease. The snow would melt. The storms would pass. The fire danger would shift. The rivers would crest and fall. But the lesson would remain. The atmosphere had shown how connected its extremes could be. And if scientists are right, this will not be the last time one wave makes an entire country feel like it is living through multiple seasons at once. Chapter 10. The forecast system was not built for this. Modern weather forecasting is one of the most impressive scientific systems humans have ever built. Every day, satellites scan the planet from space. Weather balloons rise through the atmosphere, measuring temperature, pressure, wind, and moisture. Radar stations track storms in real time. Ocean buoys report wave heights and sea surface temperatures. Aircraft collect data as they cross continents. Supercomputers take all of that information and use it to simulate the atmosphere hours and days into the future. The result is something most people barely think about. A forecast. A number on a phone. A warning on a screen. A map on television. A push alert telling someone to take shelter, avoid travel, prepare for heat, or watch for flooding. But behind that simple message is an enormous machine. And on days like this, that machine is tested. Not because meteorologists do not understand what is happening. They do. Not because the warnings are useless. They are not. The problem is that the atmosphere can sometimes produce risk in a way that does not fit neatly into the categories humans created to explain it. The warning system is built around hazards. Winter storm warning, blizzard warning, heat advisory, excessive heat warning, severe thunderstorm watch, tornado warning, red flag warning, flood watch, flash flood warning. Each product has a purpose. Each one is designed to communicate danger quickly. Each one has its own criteria, its own audience, and its own emergency response chain. That system saves lives. A tornado warning tells people to get underground or into an interior room. A blizzard warning tells drivers not to travel. A red flag warning tells people to avoid anything that could spark a fire. A heat advisory tells vulnerable people to stay cool and hydrated. A flood warning tells people to avoid rising water. These messages are clear because they are specific. But the atmosphere itself is not divided that way. The atmosphere does not create a heat advisory in one box, a blizzard warning in another, a tornado watch in another, and a fire warning in another. It creates patterns, large patterns, connected patterns, patterns that can activate multiple hazards at the same time. That is where the challenge begins. On this day, people in different regions were receiving different warnings from different offices, each one focused on the threat most immediate to them. That was necessary. A person in Wyoming did not need a long lecture about East Coast heat while driving through a whiteout. They needed to know whether the road was safe. A person in Boston did not need details about fire weather in Texas before deciding whether an elderly relative had cooling. They needed to know how dangerous the heat would be. A person in Kansas did not need a full explanation of the jet stream while a tornado warning was active. They needed shelter. Local warnings must remain local enough to save lives. But once the immediate safety message is delivered, there is another layer people need to understand. The system layer. The reason these hazards are happening together. Because without that larger explanation, the public experiences the day as chaos. One headline says snow. Another says heat. Another says tornadoes. Another says fire. Another says flooding. To the average viewer, it can feel like the world is simply becoming random. But it is not random. It is structured, and that structure matters. The forecast system sees it. Meteorologists see it. Researchers see it. Weather models show it. Upper air maps reveal it. Satellite loops display it. But the communication system often breaks it into separate warnings, because that is how public safety messaging has evolved. This creates a gap. The science understands the connection, The warnings communicate the local danger, but the public may never receive the full story tying the hazards together. That gap is becoming more important as compound extremes become a bigger concern. A compound extreme is not just a bad event, it is the overlap of multiple risks. Heat plus drought, rain plus saturated soil, wind plus dry fuel, storms plus vulnerable infrastructure, snow plus travel corridors. Multiple regions under different threats at the same time. These overlaps are harder to communicate than single hazards. A tornado warning is urgent and direct. But how do you warn an entire country that one atmospheric wave is producing 5 different hazards across thousands of miles? How do you explain that a blizzard in one region and a heat dome in another are not contradictions but connected outcomes? How do you tell people that the risk is not only local but systemic? This is one of the communication problems of modern weather. The atmosphere is giving us connected events. The public is receiving disconnected messages. That does not mean forecasters are failing. In fact, the opposite is true. Local forecast offices often do remarkable work under pressure. They issue warnings, update discussions, coordinate with emergency managers, brief local officials, answer media questions, and monitor rapidly changing data. The issue is architecture. The warning system was designed to handle specific hazards, but the atmosphere is increasingly forcing people to think across hazards. Imagine an emergency manager trying to plan resources during a day like this. One region needs snow response, another needs heat response, another needs storm shelters, another needs fire crews ready, another needs flood monitoring. Transportation networks may be affected in multiple places. Power demand may rise in one region while storms threaten power lines in another. Hospitals may prepare for heat illness in the east while tornado injuries become possible in the plains. Fire crews may need prepositioning in the southwest while flood rescue teams remain alert in the Midwest. This is not just weather. This is coordination. And coordination becomes harder when multiple hazards unfold at once. The public also faces warning fatigue. When people receive too many alerts, they may stop paying attention. If every day feels like a warning day, the brain begins to filter the warnings out. That is dangerous because some alerts require immediate action. The challenge is to communicate seriousness without creating numbness, to explain danger without exaggeration, to show connection without making people feel helpless. That is why storytelling matters. A good weather story does more than list warnings. It helps people understand the pattern. It shows cause and effect. It explains why snow, heat, storms, fire, and flooding can happen on the same day without making the viewer feel lost. That is the role long-form weather documentaries can play. They do what a short forecast cannot always do. They slow the pattern down, they zoom out, they connect the pieces. They show the atmosphere as a system, and that systems view is becoming necessary. Because the future of weather communication may not be only about telling people what hazard they face. It may also be about teaching people how to recognize the atmospheric setups that create those hazards. When viewers understand ridges, troughs, jet stream waves, moisture transport, drought feedbacks, and heat domes, they become more prepared. They know what questions to ask. They understand why warnings matter. They see the map differently. A heat wave becomes more than a hot day. A blizzard becomes more than snow. A tornado outbreak becomes more than storms. A red flag warning becomes more than dry wind. A flood watch becomes more than rain. Each one becomes a sign of a larger pattern. This is not about turning every viewer into a meteorologist. It is about giving people enough understanding to recognize when the atmosphere is entering a dangerous mode. Because days like this are not only remembered by their impacts, they are remembered by the failure or success of communication. Did people understand the danger? Did they act early? Did they connect the warning to their own decisions? Did they know what to do before conditions worsened? The forecast system can see remarkable things now. It can often identify dangerous patterns days in advance. But the final step is human. A warning only matters if people understand it, trust it, and respond. And that is where days like this reveal the next challenge. The science is advancing. The models are improving. The warnings are better than ever. But the atmosphere is also showing us patterns that require a new kind of public understanding, one that can hold two truths at the same time. Your local warning matters, and your local warning may be part of something much larger. The blizzard, the heat dome, the tornado outbreak, the fire weather, and the flood risk were not competing stories. They were one story told in 5 regional languages. And once that becomes clear, another question rises. If this wave can do all of this today, what happens when the next wave forms? Chapter 11. When the next wave forms, every weather pattern ends. The heat breaks, the cold retreats, the storms move east, the wind dies down, the snow melts, the rivers crest, the fire danger shifts. Eventually the atmosphere changes shape, and the map looks calmer again. That is one of the reasons people underestimate major patterns. Once they pass, normal life returns quickly for those who were not directly damaged. The sky clears, temperatures fall back into range, roads reopen, warnings expire. People move on, but the atmosphere does not stop. It resets, and then it begins building again. Somewhere over the Pacific, a disturbance forms. Somewhere over the Rockies, pressure begins to change. Somewhere over the Atlantic, a ridge strengthens or weakens. Somewhere in the tropics, heat and moisture shift. Somewhere in the jet stream, a small bend starts to grow. At first, it may not look important. A slight dip in the flow, a small ridge on a model map, a hint of stronger winds aloft, a warm anomaly appearing several days out, a moisture plume beginning to organize. But meteorologists know that large patterns often begin quietly. The next wave does not arrive with a headline. It appears first as a shape, and the shape is what matters. When forecasters look ahead, they are not only asking whether it will rain in one city or snow in one mountain range. They are asking larger questions. Where is the jet stream? Is it flat or wavy? Is a trough digging into the west? Is a ridge building over the east? Is moisture being transported north? Is drought still present beneath the pattern? Are soils saturated in the flood-prone areas? Are sea surface temperatures supporting stronger ridging? Is the pattern moving quickly or slowing down? These questions determine whether a future weather setup remains ordinary or becomes dangerous. The next wave may not look exactly like this one. It probably will not. Weather rarely repeats perfectly. The trough may form farther west or farther east. The ridge may center over the southeast instead of the northeast. The storm corridor may shift into Iowa, Illinois, Oklahoma, or the Ohio Valley. The fire threat may concentrate in New Mexico, Arizona, Texas, or California. The flood risk may move north or south depending on where the moisture stalls. But the mechanism can be similar. A bend in the jet stream grows. Cold air moves one way. Warm air moves another. Moisture is pulled into a boundary. Dry air descends across vulnerable land. The pattern slows. Hazards begin to overlap. That is why understanding one event helps prepare for the next. The names of the states may change. The physics does not. The next time a deep trough digs into the western United States while a strong ridge builds downstream, forecasters will look for the same warning signs. Late season or high elevation snow on the cold side. Heat beneath the ridge. Severe storms where warm, moist air collides with upper level energy. Fire weather along the dry, windy flank. Flooding where storms repeat over wet ground. This is the template. Not every ingredient will appear every time. But when enough of them overlap, the pattern becomes loaded. For viewers, the first sign may come from local forecasts using phrases that sound familiar. Unseasonably hot. Record-challenging temperatures. Strong to severe storms. Critical fire weather. Heavy rainfall potential. Late season snow. Major heat risk. Multiple rounds of storms. Those phrases matter. They are not decoration. They are signals. Weather offices use careful language. Forecasters do not casually call something unusual, dangerous, or record-challenging without reason. When several offices across different regions begin using strong language at the same time, it can be a sign that the larger atmosphere is entering a connected extreme pattern. That does not mean panic. It means pay attention. A prepared person does not need to be afraid of every forecast model run, but they should know when the pattern deserves respect, because the next wave will give warning signs. Most large-scale patterns do. The question is whether people will recognize them. 5 to 7 days ahead, models may show a ridge building. 3 to 5 days ahead, confidence may increase. 2 days ahead, local offices may begin highlighting hazards. 1 day ahead, watches and warnings may appear. On the day itself, radar, satellite, surface observations, and local conditions determine the final impacts. The timeline is there, but people need to know how to use it. For heat, preparation means checking cooling options before the hottest afternoon. It means knowing who is vulnerable. It means changing work and exercise plans. It means recognizing that early heat can be dangerous, even if it does not last long. For snow and blizzard conditions, preparation means respecting road closures, carrying emergency supplies, and understanding that mountain weather can turn quickly even in spring. For severe storms, preparation means having a shelter plan before warnings are issued. It means knowing where to go, how to receive alerts, and what to do if storms arrive after dark. For fire weather, preparation means preventing ignition before a fire starts. It means avoiding outdoor burning, securing equipment, and understanding that the danger exists even when the sky is clear. For flooding, preparation means never crossing flooded roads, watching repeated rainfall, and understanding that water can rise after the heaviest rain has already passed. Each hazard has its own actions. But the pattern has one larger message. Do not wait until the disaster is visible. By the time flames appear, the fire environment may already be extreme. By the time water crosses the road, the crossing may already be deadly. By the time the tornado warning sounds, shelter time may be limited. By the time heat reaches its peak, vulnerable people may already be under stress. By the time blizzard conditions develop, travel may already be unsafe. The advantage of modern forecasting is time. The danger is wasting it. This is where the next wave becomes more than a meteorological idea. It becomes a planning problem. If the atmosphere is capable of producing multi-hazard patterns more often, then communities need to think beyond one warning at a time. Families need plans that cover more than one hazard. Cities need heat response and flood response and storm response. Rural areas need fire prevention and severe weather communication. Transportation agencies need to consider how weather in one region affects movement in another. The next wave may not affect everyone, but it will affect someone. And when it does, the people who understand the pattern will have an advantage. They will see that a heat dome is not only about heat, it may also mean storms along the edge. They will see that a western trough is not only about mountain snow, it may also mean plain severe weather and fire danger on the dry side. They will see that moisture transport is not only about rain, it may also mean flooding if storms repeat. They will read the map as a connected system. That is the shift. From reacting to weather as isolated events to recognizing the architecture behind them. The next wave is not a monster hiding in the distance. It is a natural part of the atmosphere, but in a warmer, more volatile, more moisture-loaded, more drought-stressed world, ordinary atmospheric patterns can produce extraordinary consequences when they align with vulnerable conditions. That is the key. The wave does not act alone. It meets the world beneath it. Cities, farms, forests, roads, rivers, power grids, communities. The same physics that has always shaped weather now interacts with systems built for an older range of extremes. And when the next wave forms, the question will not simply be what the atmosphere does. It will be what it does to the places we have built beneath it. That is why the end of one pattern is not the end of the story. It is only a pause. The wave breaks. The map calms. The warnings expire. And then the atmosphere begins arranging the next test. Chapter 12. The new normal nobody is ready for. The phrase new normal is used so often that it can lose its meaning. People hear it and think it means every day will be catastrophic. That is not true. Most days will still feel ordinary. There will still be calm mornings, mild afternoons, gentle rain, cool nights, and long stretches when nothing dramatic happens. Weather will still have quiet periods. Seasons will still exist. Not every storm will be historic. Not every heat wave will break records. Not every dry spell will become a fire disaster. But a new normal does not mean constant disaster. It means the boundaries have shifted. It means the atmosphere can reach extremes more easily than before. It means patterns that used to be rare may appear more often. It means combinations that once seemed unusual may become familiar. It means the background conditions beneath ordinary weather systems are changing. That is what this day revealed. Not the end of the world. Not random chaos. Not a mystery beyond science. Something more subtle and more important. A shift in what the atmosphere is capable of doing when the pattern lines up. A blizzard in May does not prove the climate is cooling. A heat wave in May does not prove every summer day will be unbearable. A tornado outbreak does not prove every storm is stronger. A fire weather day does not mean every dry region will burn. A flood risk does not mean every rainfall becomes disaster. But when all of these hazards appear together, connected by one amplified wave, the signal becomes harder to ignore. The atmosphere is showing its range. And that range is becoming more consequential. This is the difference between weather and climate. Weather is the event. Climate is the background that shapes the event. A single day cannot tell the whole story. But many days, many patterns, many records, many overlapping extremes, and many scientific studies begin to reveal a direction. That direction is what scientists are watching. A warmer atmosphere holds more moisture. That can increase the potential for heavier rainfall. Warmer baseline temperatures raise the ceiling for heat waves. Droughts can intensify faster when heat increases evaporation. Dry fuels can become receptive earlier. Snowpack can become more variable. Storm tracks can shift. Large-scale atmospheric waves can interact with these changing backgrounds in ways that create compound risk. This does not make every event simple to explain. The atmosphere remains complex. Natural variability still matters. Ocean cycles matter. Seasonal transitions matter. Random storm-scale details matter. The exact location of a boundary or the timing of a cloud break can still change outcomes dramatically. But complexity is not an excuse to ignore the pattern. The pattern is visible, and the pattern says that many communities are now facing combinations of hazards they were not fully built to handle. That is the part nobody is ready for. Not because people are careless, but because most systems were designed around the past. Roads were built using historical flood assumptions. Power grids were built around older heat demand patterns. Crops were planted based on familiar seasonal timing. Fire response systems were staffed around traditional fire seasons. Public health messaging was built around summer heat, not sudden major heat in spring. Emergency plans often treat hazards separately because that is how disasters were categorized for decades. But the atmosphere is increasingly presenting hazards together. That is the challenge. A city may have a heat plan, but is it ready for heat arriving earlier than usual? A rural county may have a fire plan, but is it ready for extreme fire weather outside the traditional peak season? A mountain state may have winter road protocols, but are travelers prepared for blizzard conditions in late spring? A plains community may have tornado shelters, but what happens when storms are followed by flooding rainfall? A farming region may prepare for drought, but what happens when drought, heat, hail, and flood risk all occur within the same growing season? The new normal is not one disaster. It is overlap. And overlap is harder to manage. It strains attention. It strains budgets. It strains emergency services. It strains infrastructure. It strains trust. People can understand one warning, but when warnings pile up, they can feel overwhelmed. Some may tune out. Others may fall into fear. Others may search for simple explanations that are easier to emotionally process than complex atmospheric physics. That is why clear storytelling matters more than ever. People do not need panic. They need understanding. They do not need every weather event exaggerated. They need help recognizing when the pattern is genuinely dangerous. They do not need conspiracy. They need physics. They need to know that the blizzard and the heat wave can be connected without anything mysterious happening. They need to know that a fire weather warning before a fire starts is still serious. They need to know that early heat can be more dangerous than it looks. They need to know that flooding can occur far from where the heaviest rain first fell. They need to know that the jet stream is not an abstract idea. It is one of the main steering systems of their daily lives. This is the kind of weather literacy the future requires. Not advanced mathematics. Not expert-level meteorology. Just enough understanding to see the system. To know that when a deep trough digs into the west and a strong ridge builds in the east, the middle of the country may become volatile. To know that when drought sits beneath strong wind, fire danger can escalate. To know that when heat arrives early, the body may not be ready. To know that when storms repeat over the same area, flooding can grow even without one massive storm. To know that when warnings appear across multiple regions at once, the atmosphere may be operating as one connected pattern. That understanding changes how people respond. It turns passive viewers into prepared observers. It turns weather from noise into information, and it gives people a way to act before the worst conditions arrive. Because the future will not be experienced as a graph. It will be experienced as days. A day when the power grid strains under heat. A day when smoke appears on the horizon. A day when a storm warning interrupts dinner. A day when a road disappears underwater. A day when snow closes a mountain pass long after winter was supposed to be over. A day when the local weather feels strange and then the national map reveals why. That is how climate change enters daily life, not as a distant global average, but as altered odds, shifted seasons, stronger overlaps, more loaded backgrounds, more days when the atmosphere seems to be speaking several languages at once. And still, the message is not hopeless. Understanding creates power. Forecasting creates time. Preparedness saves lives. Better communication reduces confusion. Better infrastructure reduces damage. Better planning helps communities adapt. The atmosphere may be changing, but people are not helpless beneath it. The first step is seeing the pattern clearly. This day gave us that chance. It showed what one amplified wave can do. It showed how winter and summer can appear on the same map. It showed how storms, fires, floods, snow, and heat can be connected. It showed how local disasters can be part of a continental system. And it showed why the next generation of weather awareness must be bigger than the daily forecast. The wave eventually moved on. The heat faded. The snow began to melt. The storms weakened. The fire danger shifted. The rivers continued their slow response. The headlines changed. But the atmosphere did not forget how to create the pattern. It will happen again. Maybe not tomorrow. Maybe not in the same places. Maybe not with the same combination of hazards. But somewhere, sometime, another wave will amplify. Another ridge will build. Another trough will dig. Another region will heat. Another region will flood. Another landscape will dry. Another storm zone will organize. And people will once again ask why so much is happening at the same time. When that day comes, the answer will not be hidden. It will be on the maps, in the warnings, in the shape of the jet stream, in the connection between the land and the sky. The new normal is not that every day becomes extreme. The new normal is that when extremes happen, they may increasingly happen together. And the people who understand that will be the people best prepared for what comes next. So the final lesson of this day is simple. Do not look at the weather as separate pieces. Look for the pattern, because the pattern is the story. And the next time the atmosphere decides to bring every season at once, the warning will not begin with the first disaster. It will begin quietly, days earlier, as a wave in the sky. By the end of the week, the map will look calmer. The warnings will expire one by one. The snow in Wyoming will begin to melt into the mountain streams. Roads that were closed by whiteout conditions will reopen. Drivers will move through the same corridors again, passing through landscapes that only days earlier looked like the middle of winter. On the East Coast, the heat will ease. The same cities that felt trapped under early summer temperatures will feel the relief of a cooler wind. Air conditioners will shut off. Windows will open. People will step outside and say the weather finally feels normal again. Across the plains, the storms will move on. The radar screens will quiet. Tornado watches will disappear. The emergency alerts will stop. Communities will begin assessing what happened, what almost happened, and what could have happened if the strongest storms had tracked just a few miles differently. Across the southern high plains, the fire danger will shift. The wind will weaken, humidity will recover. Fire crews will stand down from the highest level of concern. The landscape will still be dry, but for the moment, the atmosphere will no longer be pushing it toward ignition. And in the flood zones, the water will continue doing what water always does. It will move downhill. Creeks will drain into rivers. Rivers will carry the memory of the rain downstream. Some places will recover quickly. Others will watch the water rise even after the clouds are gone. That is how weather events end. Not all at once. Not cleanly. But piece by piece. The sky clears before the rivers fall. The wind fades before the fire risk disappears. The snow stops before the roads are safe. The heat breaks before the health impacts are fully counted. And then, for most people, the story fades. The news cycle moves on. The next headline arrives. The strange day becomes something people mention in passing. Remember when it snowed in Wyoming while the East Coast was under heat? Remember when tornadoes, fires, floods, heat, and snow were all on the same map? Remember when the atmosphere seemed to lose track of the seasons? But for scientists, meteorologists, emergency managers, and everyone paying close attention, the story does not end when the warnings expire. Because the real story was never only the snow. It was never only the heat. It was never only the tornadoes, the fire weather, or the flooding. The real story was the pattern. A giant wave in the atmosphere stretched across the continent. One side of that wave pulled cold air south and turned spring back into winter. Another side pushed heat north and made May feel like July. Between them, storms formed. Along the dry flank, fire danger grew. Where moisture repeated over wet ground, flooding became possible. 5 hazards. 1 system. That is the lesson. The atmosphere was not acting randomly. It was acting as one connected machine. And once you understand that, the entire day looks different. The Wyoming blizzard was not just a mountain snowstorm. It was the cold face of the wave. The East Coast heat was not just an early hot spell. It was the warm face of the wave. The plains tornado threat was not just another severe weather day. It was the collision zone of the wave. The southern fire danger was not just a dry, windy afternoon. It was the drought-loaded flank of the wave. The flooding was not just heavy rain. It was the moisture side of the wave repeating over vulnerable ground. Everything was connected. That does not mean every event was historic by itself. That is important. A single snowstorm does not prove anything. A single heat wave does not prove anything. A single tornado outbreak, fire weather day, or flood threat does not prove anything alone. But when multiple extremes appear together, linked by the same atmospheric structure, the pattern deserves attention. Because this is the kind of event that exposes how weather is changing from isolated hazards into overlapping systems of risk. And overlapping risk is harder to prepare for. It is easier to understand one danger at a time. One storm, one fire, one flood, one heat wave, one blizzard. But the atmosphere does not promise us one danger at a time. It can create several. It can stretch emergency systems across regions. It can make one part of the country too hot while another is too cold. It can create too much water in one place and not enough in another. It can make the same week dangerous for drivers, farmers, firefighters, hospital systems, power grids, and families in completely different ways. That is the future challenge. Not endless disaster. Not everyday extreme, but more days when extremes overlap. More days when the background conditions are loaded before the trigger arrives. More days when a single wave in the jet stream can reveal weaknesses across an entire continent. And that is why learning to read the pattern matters, because the warning signs usually appear before the disaster does. A ridge begins building. A trough begins digging. Moisture starts moving north. A dry region sits beneath strengthening wind. A heat dome appears on model guidance. Storm energy gathers along a boundary. The atmosphere begins arranging itself, quietly. Days before the first siren. Days before the first road closure. Days before the first fire. Days before the first flood rescue. The next major pattern will not begin with a headline. It will begin as a shape on a weather map. A bend in the jet stream. A pressure pattern. A signal that most people will scroll past because nothing has happened yet. But that is when attention matters most. Before the heat peaks. Before the storm forms. Before the fire starts. Before the water rises. Before the road disappears. Modern forecasting gives us time. But time only helps if people use it. That is the reason this story matters beyond one day. It teaches us what to watch for. When a major ridge builds over one side of the country, ask what is happening on the other side. When a deep trough digs into the west, ask where the storms will form downstream. When heat arrives early, ask whether people are ready for it. When fire danger appears before flames, ask what can be prevented. When rain keeps falling over the same region, ask how much the ground can still absorb. When snow falls in spring, ask what happens when it melts. These are not questions of fear. They are questions of awareness. And awareness is the beginning of preparation. Because the atmosphere is not waiting for us to understand it. It is already moving, already bending, already shifting heat and moisture around the planet, already forming the next ridge, the next trough, the next storm track, the next dry wind, the next rainfall corridor. The wave we watched in this story will break. Every wave does. The heat will leave. The snow will melt. The storms will pass. The fire threat will fade. The floodwaters will drain. But the conditions that allowed this pattern to become so powerful will remain part of the background. The warm atmosphere, the moisture, the drought pockets, the vulnerable cities, the dry fuels, the saturated basins, the transportation corridors, the farms, the power grids, the communities built beneath a sky that is becoming harder to predict by old assumptions. That is the uncomfortable truth. We are not watching weather disappear. We are watching weather become more connected. The old way of thinking says, this is a heat wave, that is a snowstorm, that is a tornado outbreak, that is fire danger, that is flooding. The new way of thinking says, what pattern is connecting them? That question changes everything. Because when you see the pattern, you stop being surprised by the contradictions. Snow and heat on the same day no longer feel impossible. Fire and flooding in the same national forecast no longer feel random. Tornadoes forming between winter and summer air masses no longer feel like chaos. They become pieces of one machine, and once you see the machine, you can never look at the weather map the same way again. So when the next strange day arrives, remember this one. Remember the highway disappearing into snow while cities baked under early heat. Remember the storms forming in the middle. Remember the dry wind over the fire country. Remember the rivers responding to repeated rain. Remember that all of it came from one atmospheric shape. And remember that the most important warning may not be the loudest one. Sometimes the real warning is quiet. A phrase in a forecast discussion. A subtle shift in the jet stream. A ridge that builds too strongly. A trough that digs too deeply. A pattern that slows down instead of moving on. That is how these events begin. Not with disaster, with structure. And the structure is already being watched. By satellites, by radar, by forecasters, by researchers, by people learning to see the atmosphere not as separate stories but as one connected system. That is the kind of awareness this moment demands. Not panic, not denial, not confusion, awareness. Because the wave will break, but the pattern will return. Maybe next week, maybe next month, maybe later in the summer. Maybe in a different region, with a different combination of extremes. But it will return, and when it does, the question will not be whether the atmosphere can do this. We already know it can. The question will be whether we recognize it early enough, whether communities prepare, whether warnings are understood, whether people see the connection before the impacts arrive. Because the future will not always announce itself as one disaster. Sometimes it will arrive as 5 different warnings on the same map, and behind all of them, one wave in the sky. If this documentary helped you see the weather differently, subscribe for more deep breakdowns of the patterns shaping our world. And comment below with where you are watching from. Were you under the heat side, the storm side, the fire side, the flood side, or the cold side of this pattern? Because the next wave is already somewhere in the data. And when it starts to form, we will be watching